Oh my god, there is this very cool app I need to show you. I know what you're thinking. Why Windows XP? Please, XP is like the bomb. Yeah, I have here cool app. Okay, what it does is the app will take a text file and you print out the text file on screen. Damn cool, right? I'm gonna get the text file in first. Hang on. A generic name for a text file. Okay, so oh look. Okay, so it puts some text on my screen, which is a good thing, right? So far so good, it works, right? Okay, there's another text file I downloaded. Oh. What? Okay, the whole point of the demonstration was to show an exploit that I kind of made lah. I have no life, I'm so sorry. And why Windows XP? And this is actually Windows XP Service Pack 1, so it's even much older. The reason I chose this operating system is because it is just littered with so many security flaws, and that's why you have Service Pack 2 and Service Pack 3 coming out to kind of like patch up all these holes to avoid having bad guys poking in at your computer. Okay, to show you that I didn't intentionally make the program to run calculator by itself, it's actually an unintentional side effect of running that particular text file. Don't worry if none of this makes sense to you, but basically what all this code does is, if you open a file and then if you read the file. So having this function here is quite important. Going to that function, what happens is I'll allocate a buffer to keep my file stuff. Then I'll read the file one character at a time until I can read anymore. Then as I read it, I'll put it into my buffer. Once my buffer is filled, I will print that buffer out to screen. It's just like that, so easy. Okay, this function here is the most important bit, and is the vulnerable part of the whole thing. At this point in time, I think it is better if I explain how a computer kind of works, at least briefly. Right, I'm going to try my best. Normally when you run a program or you run an app or a software, right, they are mostly just a sequential list of instructions for your CPU. You can imagine like you have a grocery list. Then you see, oh, I need to get bread first. Then I look for bread. Then I move on to the next thing in the list. I need to get butter. I look for butter. Yeah, you kind of get it, right? Okay, let me draw you something. Now here's a very simplified view of what the program is supposed to look like lah. It's a sequential list of instructions, and then the numbers over here, they are the address of the instruction, basically where the instruction resides in the memory. In the CPU, there is a very special number that it stores. It's called the instruction pointer, and this will be symbolized by my finger. So the instruction pointer is basically just a number to tell the CPU where to look for the next instruction. So if my instruction pointer says 2, then you point to 2, and then you execute what's at location 2. So if location 2 says add 1 to 2, then it would add 1 to 2 and store somewhere, something like that. Just so you know, normally programs don't start at 0, and the address numbers are usually much bigger than this, just for simplicity lah. Anyway, this is how a normal program will go. You start from the top, execute, then you increment the pointer, then execute again, increment pointer, execute, increment pointer. You can see it's a very systematic way of telling the CPU what to do. I think most, if not all, of the instruction set architectures nowadays have provisions to allow the CPU to make jumps as they execute the program, and also to call subroutines. Subroutines are basically a set of tasks or instructions that are frequently used. So instead of typing them again and again and again as and when I need them, might as well I just put this set of instructions in its own bit of memory somewhere. So when I need them, I just have to call this subroutine. You see what I mean? In my program here, 8 to 11 is my subroutine. Instruction pointer starts at 0. Then it goes to 1, then 2, then 3, then 4. Now 4 has this very special instruction called call. Here it says call memory 8. What you do is you set the instruction pointer to 8, and then the pointer will point to 8 at the next instruction cycle. Then you run from 8 to 9 to 10 to 11, and then you reach this return. Return instruction just tells the pointer to go back to the instruction immediately after the call instruction, which is 5 lah. At this point in time, you may be wondering, how does the pointer know to go back to 5 after it has encountered this return instruction? Because I didn't store it anywhere. Actually, I did. And this is where I'll introduce the stack. As I call something, I will push the next instruction address to the stack. So it's 5, right? I'll push 5 to my stack. This is my stack. Then you'll move the pointer to 8, to 9, to 10, to 11. Then sees a return. You go to the stack and see, oh, there is a 5. I will pop the 5 out of the stack, put it to my pointer, so my pointer knows to go to 5. Very smart, right? Okay, there's one more thing I need to tell you, and that every time you declare variables in your functions or your subroutines, right, all these variables, at least the address lah, it will be pushed to the stack as well. If my subroutine has variables in it, the stack will not only has the return address, but also the addresses of my variables. And that is very important. Now going back to the exploit. Now it's high time for me to show you what actually were in those two text files. Now the first one that I opened, the one that didn't cause calculator to pop out all of a sudden, this is just a normal text file. You can see it's just a normal text file. The other one wasn't really a text file, but a specially crafted file to exploit that vulnerability that I showed. The size of the file is at least big enough to overflow that buffer that I created. You can see here, if you can even see it, it says calc.exe. So somewhere, somehow, I'm referring to this string here to run calculator. In any Windows, right, if you were to run the command calc.exe, you'll run calculator. So somewhere, I'm running this command. Why does the file size even matter? And why are there so many C's here? Okay, all these C's here, they're more like a junk data, just to pad out the whole thing for a specific purpose. Now here is what we normally call a disassembler or a debugger or something like that. I open my program, that cool app, right, and put it into here, and it will show you all the machine code. Basically, this is the list of instructions that the CPU has to run. Of course, the most important point now is to go to the instruction right before calculator appears. So I'll let it run, and then I'll type in the bad text file, and I'll let it reach the return. Okay, so here you can see RETN, the return instruction. Remember what I said about the return instruction? Return instruction just tells the pointer to go back to the instruction immediately after the call instruction. The return instruction will look at the stack, and it will take out a number from the stack. That number becomes the instruction pointer. Okay, so right now highlighted at the stack is this number. It's 0022F620. So this is now the return address. When I say return and I see this number, that means I must go back to that number. So let's find out what is at this number. So right now in my stack, you can see that at that address, right, it has this bunch of weird stuff going on. We don't really know what is it, but you can see if I move this to the side a bit, calc.exe suddenly appear. Very suspicious. Okay, we let it run one instruction forward and see what happens. My instruction pointer is now at 22F620, what we saw just now lah. Here says there's a no operation, nothing to do. We go on. We push 5 to the stack. 5. Why 5? Don't know. Then we push this. This is the address to the string calc.exe. Then the important bit comes here. Call kernel32 winexec. So this one is a function found in some of the Windows doohickey libraries that is going to execute programs. And what I'm executing? calc.exe. And that's why the calculator appeared. So if I let this run some more, oh look, calculator just appeared. And so what was the point of that big length of C's that you saw just now? Remember this? All these C's, what are those for? These are for padding. Now this file is carefully crafted such that the instructions are placed here. There are enough C's, enough CC's, such that at a certain memory address, this number appears, 0022F620. Sounds familiar? Okay, so right now highlighted at the stack is this number, is 0022F620. So this is now the return address. What I'm doing is I'm overflowing this buffer such that it overwrites the return address. So it returns to another address instead of the original address. I'm changing the stack. Basically, remember this number, I'm erasing it and I'm replacing it with something, but I have to fill all the way down to erase it. That's why I have all this padding. Now the reason why I chose Windows XP, like I said, is because of the security flaws that it had, at least for SP1. SP2, SP3, they are more patched up. But it's just a proof of concept of how exploits normally work lah. At least there are more clever ways to do it. And nowadays, for modern day operating systems, right, they employ a lot of techniques such as address space randomization. You saw just now that I had to target exactly 0022F6 something. In the newer operating systems, right, it was made such that the address space of the entire program shifts randomly every time you start it or you reboot your computer, so your exploit cannot always work. So that's one way. And another way is data execution prevention in the more modern Windows. And what it does is it marks all the executable instructions as executable and the rest as non-executable. That includes the stack and the heap. The heap is another bit of memory, but it marks these 2 bits of memory as not instructions. What I did just now was I smashed the stack. So I overflowed the buffer, I smashed the stack, and then I made it point back to itself and I let it run from there. In the new Windows, you can't really do that. You need to go through a roundabout way to actually do that. So as I said before, keep your softwares up to date. When if you want the source code to all these things, you can get it down there, but I don't think it'll even work for now. Unless you have Windows XP lying somewhere, then you can probably play with it. I will see if I can do something more crazy. I don't know. When I see return and I see this, oh, I'm using my finger, I'm so stupid.